Good morning. This is the lecture number third of the analog electronics. The topic is the application of semiconductors. PN diode application, photodetectors. When the light illuminates the PN junction, the photon energy release free electrons and holes. They are referred to as photoelectric and photoholes. The applied voltage separates the photocarriers, attracting electrons toward plus and holes toward minus. Here, electrons represented by the plus and holes toward the minus. As long as the light is on, so there is a current flow through the PN junction. And we know that the current flow in semiconductor device due to the holes and electrons. Holes are positive charge carriers and electrons are negative charge carriers. And this is the circuit diagram of a simple PN junction which is biasing by the forward bias voltage. Next, negative resistance device. Some devices have the negative resistance in the semiconductor device. In negative resistance device, it is a device which exhibits a negative incremental resistance over a limited range of VI characteristics. It is two types: current control type device and voltage control type device. So for example, the UJT and BJT semiconductor device are the current control device, and the other device, tunnel diode, etc., are the voltage control device. In current control device, VI curve is a multi-value function of voltage and single value function of current. For example, UJT and PN diode. These are the two devices which have the current controllable type device. Next one is the voltage control device. VI curve is a multi-value function of current and single value function of voltage. For example, SCR and tunnel diode. These are the voltage control type device. Next semiconductor device is the tunnel diode. What is the tunnel diode or Isaki diode? It was introduced by Leo Isaki in 1958. This diode heavily doped in PN junction. This is not a simple PN junction diode, but this is heavily doped PN junction diode. Impurity concentration is 1 part in 10 to the power 3 as a compared to 1 part in 10 to the power 8 in PN junction diode. This is the ratio of the impurity concentration in the tunnel diode. Width of the depletion layer is very small in this tunnel diode, about 100 Armstrong, and it is generally made of germanium semiconductor and compound semiconductor, just like a gallium arsenide. It showed tunneling phenomena And circuit symbol of tunnel diode is like this. Here are two terminals. One is anode and second is cathode. Anode is positive terminal and cathode is the negative terminal. Negative terminal. So tunnel diode is a particular specific type diode. And what is the tunneling in the tunnel diode? So classically, carriers must have energy at least equal to potential barrier height to cross the junction. This is the condition for crossing the junction of the charge carriers. The carrier must have a energy at least equal to potential barrier. It means carrier have the energy equal to the potential barrier. If this condition is satisfied, then the charge carriers easily cross the junction. Otherwise, not possible this phenomena. What, according to quantum mechanics, there is finite probability that it can penetrate through the barrier for a thin width. This phenomena is called tunneling, and hence Esaki diode is known as the tunnel diode. Because tunnel diode have the tunneling effect. And what is the tunneling effect? According to quantum mechanics, there is a finite probability that can penetrate through the barrier for a thin width. This phenomena is known as the tunneling, and hence the Esaki diode known as the tunnel diode. So the name is tunnel diode because it have the tunneling effect in principle of working condition. Here we see the characteristics of tunnel diode. We draw the graph between the forward current versus forward voltage. So we see here the graph is like this as shown in this figure, and there some points on the graph. Here is the negative resistance region. This is the negative resistance region. This is the valley point, and with respect to valley point voltage, the current is valley current, and this is a peak voltage here. This point, the current with respect to this point is IP peak current. So the IP is the peak current here, and IB is the valley current, and VP is the peak voltage, VB valley voltage, and VF peak forward voltage. So this graph shows the characteristics of tunnel diode, or we can say that the graph between the current versus voltage for different value of current and different value of with respect to voltage. You see in this graph, initially the current increase with the voltage, and a maximum point at the peak point, the we increase the voltage, but the current is not increased, and current is the decrease with increasing the voltage. So at the value point, it stops the current to decreasing, and after this value point, the current is increased with increase the voltage. So this is the graph between the current versus voltage of the tunnel diode characteristics. Here this is the energy band diagram. Energy band diagram of PN junction in thermal equilibrium, in which both N and P region are degenerately docked. You see in this two energy level, one is EC and second is EB. Here is the conduction band and here is the valence band. The difference between the conduction band and the valence band is the called as a forbidden energy gap or band gap energy. So here is the space charge region. Basically, space charge region is generated across the junction of a PN junction device. Mostly there are immobile charge carrier across the junction. This is the space charge region or depletion region. There are immobile charge carrier deposit across the junction. At the zero bias condition, when we applied the voltage a zero across the any PN junction diode or PN junction device. So simplified energy band diagram and VI characteristics of the tunnel diode at zero bias. Zero current on the VI diagram. You see here the dot present the zero current and all energy state are filled below EF on both sides of the junction. So this is the for relation between the conduction band and valence band, the forbidden energy gap and the energy band diagram representation for the zero bias condition. At small forward voltage, now we applied the very small forward voltage across the junction. So we see here in this graph I versus voltage, current versus voltage. The this graph show the very small increase the current with increasing the voltage, and this is show the energy band diagram of for a small forward voltage. Simplified energy band diagram and VI characteristics of the tunnel diode at a slight forward bias. Electrons in the conduction band of the N region are directly opposite to the empty state in the valence band of the P region. So, a finite probability that some electrons tunnel directly into the empty state, resulting in forward bias tunneling current. So, this is the concept about the small forward bias when applied to a tunneling diode or PN junction diode. Now we take the maximum tunneling current. Simplified energy band diagram of VI characteristics of the tunnel diode at a forward bias producing maximum tunnel current. The maximum number of electrons in the N region are opposite to the maximum number of empty state in the P region. Okay, hence tunneling current is maximum. This is the concept. This is the region of maximum tunneling current. The maximum number of electrons in the P region, sorry, in the N region are opposite to the maximum number of empty state in the P region. Because we know that in P region, the maximum or majority charge carriers are holes, what and N region, the majority charge carriers are electrons. So hence tunneling current is maximum in this condition. At forward higher voltage, a simplified energy band diagram and VI characteristics of the tunnel diode at a forward bias for which the diffusion current dominates. No electrons on the N side are directly opposed to the empty state on the P side. Okay, so in N side there is the maximum charge carriers hole, and but in P side maximum charge carriers holes. The tunneling current is zero. In that condition, the normal ideal diffusion current exists in the device. Next, at reverse bias voltage, that is the next condition. You see in this graph here current versus voltage. In quadrant third, the the current versus voltage, what is the value of current with respect to voltage in quadrant third at the reverse bias voltage condition. A simplified energy band diagram of a tuned diode with a reverse bias voltage and VI characteristics of a tunnel diode with a reverse bias voltage. Electrons in the valence band on the p side are directly opposed to empty state in the conduction band on the n side. Electrons tunnel directly from the p region into the n region. The reverse bias current increase monotonically and rapidly with reverse bias voltage. This is the conditions for reverse bias voltage of the tunnel diode. Now we draw the equivalent tunnel diode circuit. We see here a simple one series resistance and one parallel resistance and one inductance and one is the capacitance. This is the equivalent circuit of the tunnel diode, which is represented by the resistance, inductance and capacitance. This is the equivalent circuit of tunnel diode when bias is negative resistance region. We know that the tunnel diode have the negative resistance region. So at higher frequency, the series R and L can be ignored at the higher frequency. R resistance and inductance can be ignored at the higher frequency. Hence, equivalent circuit can be reduced to parallel combination of junction capacitance and negative resistance. So this is the equivalent circuit can be reduced by the only two components, by the resistance and capacitance, which are connected parallel to each other. So this is the tunnel diode equivalent circuit. Next device, semiconductor, is Zener diode. This is the also a PN junction diode, but it have the some specific concept in operation and working operation are different as compared to tunnel diode and simple PN junction diode. We represent the simple Zener diode by this symbolic symbol Here is the also two terminal anode and cathode. Anode is the positive terminal and cathode is the negative terminal. Here IZ is the Zener current and BZ is the Zener voltage. Basically, Zener diode is the used as a controlling the control device as a huge Zener diode. A Zener diode is a diode operated in reverse wise at the peak inverse voltage PIV called a Zener voltage. We know that the simple PN junction operate in forward wise condition, what the Zener diode operate in reverse wise condition. In that peak inverse voltage PIV, and that voltage is called the Zener voltage, and that is the VZ. The common Zener voltage 1.8 volt to 200 voltage. This is the common Zener voltage, which voltage is used to control the device. Now we draw the characteristics of Zener diode. VI characteristics. VI characteristics means graph between current versus voltage. So we see here, because we know that the Zener diode operate in reverse bias condition. So here is the Zener region, because here is the Zener voltage. In that case, the Zener current rapidly increase by increasing the voltage, and here a breakdown condition occur in Zener diode, and this region is the operating region of the Zener diode. That is the third quadrant of this graph. The diode is in the reverse bias condition. At some point, the reverse bias voltage is so large, the diode break down. Okay, the reverse bias voltage is so large, the diode break down, and in that condition, the reverse current increase very rapidly. The reverse current increase dramatically, very rapidly. So this maximum voltage is called avalanche breakdown voltage, and the current is the avalanche current, which is rapidly increased with the voltage. Next, resistance levels. There are some resistance of PN junction diode devices have some resistance, and semiconductor act differently to DC and AC current. There are three type of resistance. Mostly there are three type resistance, which have the PN junction devices or semiconductor PN junction semiconductor devices, which have the three type of resistance, AC and DC. DC means direct current resistance and AC means alternating current resistance. There are three types resistance. First one is the DC or static resistance. Second one, AC or dynamic resistance. Third one is average AC resistance. So there are total three type of resistance in PN junction devices. Now, DC or static resistance. What is DC or static resistance? The resistance of a diode at a particular operating point is called the DC or static resistance diode. It can be determined using equation this. RD means DC resistance equal to BD upon ID, where BD is the DC voltage, ID is the DC current. This is the static resistance or DC resistance of the diode. What some ideal values here for the ideal diode and silicon diode, the different values given here. ID, the value of ID for ideal diode is that an ampere is 20 and 2 and BD 00 and value of RD is 00, and for the silicon diode ID is the 20 and 2 and BD value is the 0.8, 0.5 and value of RD is the 40 and 250. These are the DC or static resistance values of different ideal diode and silicon diode. Now, DC resistance of forward bias region decrease when higher current and voltage. Okay, DC resistance of forward bias region decrease when higher current and voltage. It means if the voltage and current value is high, then the resistance value is low. This is for the DC resistance. And also some values for ideal diode and silicon diode. Their ID 0, VD is -10, RD infinite. For silicon diode, ID 2 micro ohm, VD -10, and RD is 5 megaohm. DC resistance of reverse bias region, its open circuit equivalent. Okay, these are the some ideal value for ideal diode and silicon diode. Now we discuss about the AC or dynamic resistance. So what is the AC or dynamic resistance for a PN junction device? Static resistance is using DC input. If the input is sinusoidal, so the scenario will be changed. We vary the input will move instantaneous operating point up and down of a region. Thus, the specific change in current and voltage is obtained. So it can be determined using equation this. Small RD equal to change in voltage upon change in current. This is the AC or dynamic resistance for the PN junction diode. RD equal to change in voltage divided by change in current. This is the variation of voltage with the current, and so the value of resistance also change with the voltage and current. Now we find out the average AC resistance of the PN junction diode. So we see here in this graph, we take the current on the y-axis, and different change in voltage we take the on x-axis. So we see this in this graph, the current change with the voltage, or the relation between current versus voltage is like follow the linearity, because we change the current also with respect the current, the voltage also change. So the here I proportional, current proportional to the voltage. Here we see in this graph R average equal to VD upon ID, point to point. This is the very point to point. So AC resistance can be determined by picking 2 points on the characteristics curve or VI curve developed for a particular circuit. You see in this on y-axis there is a change del ID, and on x-axis there is a some voltage change del VD. So the ratio of voltage to change in voltage to change in current is the average resistance of the PN junction device. Now we come the applications of different PN junction diode. So the first and important application of the PN junction diode is rectifiers. Basically, rectifiers means in rectifiers, the AC signal convert into DC signal, or AC voltage convert into DC voltage with the help of rectifiers. Basically, to construction rectifiers, basically diodes are used to construct a rectifier device. Now rectifiers, filters and regulators, these are the different parts of the rectifiers. Half wave rectifiers, ripple factors, full wave rectifiers, harmonic components in a linear circuit, inductor filters, capacitor filter, L section filters, pi section filters, multiple L section and multiple pi section filters, and comparison of various filter circuit in term of ripple factors. Simple circuit of a regulator using Zener diode, series and shunt voltage regulators. So we design a rectifiers. Some parameters have to be familiar. What is the power supply? What is the requirement of filters, and what requirements of regulators? So power supply circuit. So first of all, we know about the power supply circuit. To achieve its purpose, a power supply must step down the voltage supplied, because we you see in this circuit we construct a rectifier circuit. So first of all, AC supply applied to the transformer, and generally transformer used as a step down type transformer. Basically, transformer are two types: step down and step up. What in for designing the rectifiers, we use the step down transformer. and next components are diodes, and some components are resistance, capacitance, inductance, etc. and a power supply circuit. So to achieve the purpose, a power supply must step down voltage supply, because the input voltage is 220 or 240 voltage AC. So we must step down this voltage, supply voltage, by using the step down transformer. Now convert AC to DC by rectifying the AC. Next, in next circuit or diode circuit, the AC signal convert into DC signal by the rectification process, and a transformer is used to step down the magnitude of the voltage from the wall receptacle. So we use the transformer as a step down type, and you see in this diagram here is the AC supply voltage applied to the this transformer. Here is the step down transformer. Here is the primary winding in this side is the secondary winding, but the number of turn in primary winding is greater than number of turn in secondary winding, because this is the step down transformer. So the number of turns are different to each winding. A transformer consists of two coils of wires, which is called primary winding and secondary winding, and have the one common iron core. Common iron core. This is the common iron core. This is the turn ratio. Here in this transformer, we take the primary winding ratio to secondary winding ratio is the 10 to 1 ratio. Turn ratio is the 10 to 1. It means number of 10 turns in primary winding and number of 1 turns in secondary winding. So the turn ratio is the 10 to 1. This is the turn ratio of primary winding to the secondary winding of the transformer device. The voltage on these two coils are related by the turn ratio. The voltage depend on the number of turn ratio of the transformer, which is the ratio of the number of turns of wire in secondary coils to that in the primary coils. So there are the two bindings, primary coil winding and secondary coil winding, and the number of turns are specified to a specified transformer. And next, after this transformer, we design a rectifier circuit. To design a rectifier circuit, we use generally 4 diodes, in which 2 diodes are forward bias connections and remaining 2 diodes are reverse bias connections. When we applied the input voltage from the supply to the transformer, and transformer step down this supply and apply to the across the diodes, 2 diodes. So terminal of positive of one diode connected to the positive terminal of the transformer, and a negative terminal of transformer connected to the negative terminals of the diodes, in which 4 diodes, 2 diodes are forward bias. It means two terminals of two diodes are connected, positive terminals of transformer, and remaining two terminals of two diodes are connected to the negative terminals of the transformer. So two diodes are forward condition and remaining two diodes are reverse condition. When two diodes are forward condition, it means two diodes are conducting one at a one times, and remaining two diodes are off condition because there is a reverse biasing condition. So like this is the first cycle of the supply. Next cycle of the supply 180 to 360. One cycle of the AC supply 0 to 180 degree, and second supply or second cycle of the AC supply 180 to 360 applied to the same manner to the two forward diodes and two reverse diodes. In that condition, in next cycle of the supply, where which two diodes are forward wise, they will be now in reverse wise, and two diodes that are in reverse wise, they will now in forward wise. So polarity is changed. Polarity, the cycle of AC supply is changed. So the polarity of diode also change. So again, forward diode are conducting two diodes, and two diodes which is reverse biasing are off. So the next cycle will come like this: two diodes on, two diodes off. Next cycle again two diodes off, two diodes on, like this. So we find out and we see the output across the resistance VA DC supply. It means the AC supply convert into DC supply with the help of circuit diagram of rectifiers. So this is the working principle of rectifiers device, which is convert AC signal into DC signals. There are some books which cover these topics. First is Principle of Electronics by author Millman and Halkias. Second is Electronic Device and Circuit, author is Bolested. There are some multi-choice questions which cover this topics, and this is very important question to understand the concept of this topic, and please you solve these questions. This is very most beneficial for you. Thank you. Thank you.